Lecture video, we're going to go over section 2.5, inverse functions. So if a function has no two ordered pairs with different first coordinates and the same second coordinate, then the function is called one-to-one. In other words, every ordered pair gets picked, every number x gets paired up with only one y. So the pairings are one-to-one. So they're all unique. So if a function is one-to-one, then it is said to be invertible, which means that it has an inverse. The inverse of a one-to-one function f is the function f to the negative first power, which we read as f inverse, where the ordered pairs of f inverse are obtained by interchanging the coordinates in each ordered pair of f. So determine whether each function is invertible and then find the inverse. So the way we find the inverse, or attempt to, is by just changing these two numbers. So flipping the ordered pairs, changing the x's and the y's. So 0, 2 becomes 2, 0. 2, 0 becomes 0, 2. 1, 0 becomes 0, 1. And 4, 6 becomes 6, 4. Now, the reason it's important that the function be one-to-one in order to be invertible is so that this doesn't happen. Notice that I have the same x with two different y's, which means this is not a function. Right? Because to be a function, every x can only get paired with one y. So therefore, this is not invertible, because the original function was not one-to-one. Because notice, I have 2 going to 0 and 1 going to 0. So that means this is not a one-to-one function, because all the x's have to go to a different y to be a one-to-one function. Okay, so if we look at the second one here, notice that all of the y's are different. So since all the y's are different, this is a one-to-one function. Therefore, this has an inverse. This is invertible. Right, another name for one-to-one. And its inverse would be 1, 1, 4, 2, 16, 4, and 49, 7. So at this point, go ahead and pause the video for a second and decide whether the other two functions here are invertible, and if they are, find their inverse. Okay, so now that you've tried those, let's go through them real quick. So this one is one-to-one because the y's are both different. So that's one-to-one, so it does have an inverse. And its inverse would be 5, 4, and 6, 5. And then the last one here, these two share the same y, so this is not one-to-one. So it is not invertible. Okay, so when you know all the ordered pairs of a function, that's the easiest way to tell if it's invertible or not. Now, if you're dealing with equations or graphs, there's a pretty simple test for that as well. And it's called the horizontal line test. So the horizontal line test, if each horizontal line crosses the graph of a function at no more than 1 point, then the function is one-to-one. So here are some different functions we've looked at already in this class. We've looked at the line. We've looked at the parabola, the quadratic function. We've looked at the square root function. And we've looked at the absolute value function. 2 of these are one-to-one, and that is the first one. The first one and the third one. The linear function and the square root function. Whereas the quadratic function, the parabola, and the absolute value function are not one-to-one. And so the reason this horizontal line test works is because if a horizontal line hits the graph more than once, then we know these share the same y. And that's what we can't do to be one-to-one. To be one-to-one, all the y's have to be different. So the first one and the third one are 1-to-1, and the second one and the last one are not 1-to-1. So we can use this idea along with our class calc app to decide if a function written as an equation is 1-to-1 or not, right? And based on what I just drew up above, you should be able to tell without having to necessarily graph these specific examples whether or not they're 1-to-1, because these all fit under one of these graphs, right? The t of x here is a square root function. So that means it looks like the third graph. So that's going to be 1-to-1. Okay, and there's actually a fairly quick and easy way to prove that something is 1-to-1. And what we do is we assume that the function has two different x values with the same y value. And then we show that if that were the case, the x's would actually have to be the same. So in this first example here, if I did t of x sub 1 equals t of x sub 2, that would be the square root of x sub 1 plus 3 equals the square root of x sub 2 plus 3. And we could try to solve for x sub 1. So if I did that, I'd square both sides. So I get x sub 1 plus 3 equals x sub 2 plus 3. And then I can subtract 3 from both sides. And we get x sub 1 equals x sub 2. So it checks out that that is a 1-to-1 function. Now the second one here is an absolute value. So based on the graphs that we already know, we should think this is probably not 1-to-1. But to prove that, we can do the same thing we just did. We assume that there is an r of x sub 1 that is equal to r of x sub 2. And what we want to prove here is we want to show that while this would work if they were equal, that there's also another option. So this would be 2 times the absolute value of x sub 1 minus 1 equals 2 times the absolute value of x sub 2 minus 1. Divide both sides by 2. So we get the absolute value of x minus 1 equals the absolute value of x sub 2 minus 1. And now remember, to get rid of the absolute values, two numbers that have the same absolute value are either the same number or they're opposites of one another. So either x sub 1 minus 1 equals x sub 2 minus 1, or x sub 1 minus 1 equals the opposite of x sub 2 minus 1. So over here we add 1 to both sides, and we get x sub 1 equals x sub 2. So one way that you could get the same y would be if they were the same. However, if we do this one, x sub 1 minus 1 equals the opposite of x sub 2 plus 1, add 1 to both sides, and we get x sub 1 equals the opposite of x sub 2 plus 2. So this shows that x sub 1 does not necessarily have to equal x sub 2 for the y's to be the same. Therefore, there are two different x's with the same y, so this is not 1-to-1. And so that's the idea. So why don't you all pause the video for a second and decide if you think these other two should be 1-to-1, and then try and use this idea to prove that what you thought was correct. Okay, so now that you've had a chance to try this, let's go ahead and talk about it. So this one is quadratic. So based on the graph number 2 up there, we should say this is not 1-to-1. And you could always graph it with your class calc app to get a good idea of what that looks like. And then we could prove that that's actually the case. So we do v of x sub 1 equals v of x sub 2. And plug those in. So 2 of x sub 1 squared minus 1 equals 2 times x sub 2 squared minus 1. And solve for x sub 1. So add 1 to both sides. So we get 2x sub 1 squared equals 2x sub 2 squared. Divide both sides by 2. And we get x sub 1 squared equals x sub 2 squared. And then we take the square root of both sides. And so what we get is we get x sub 1 equals plus or minus x sub 2. So x sub 1 could equal x sub 2, but it doesn't have to. Therefore, this is not a 1-to-1 function. And then the last one here is linear. So we should think that is 1-to-1. based on the graphs. And so we can try and prove that real quick. So h of x sub 1 equals h of sub x sub 2. Plug those in. So 4x sub 1 minus 9 equals 4x sub 2 minus 9. Add 9 to both sides. And then divide both sides by 4. And so we see that if h of x sub 1 equals h of x sub 2, x sub 1 has to equal x sub 2. So this is indeed 1 to 1. So the nice thing about this is to decide whether or not something is 1 to 1, all you really have to do is look at the graph of it. So you can just graph it in class calc and decide if it's 1 to 1. But here is a nice technique for proving if something is 1 to 1 if you ever need to use that. Okay. So now that we've talked about how to decide if something has an inverse, let's talk about how to decide if two functions are indeed inverses of each other. So the best way to do this is to use composition of functions. So the way inverses work is they cancel each other out. So what we're looking for is the identity element. So like when we talk about inverses in addition are opposites. So a plus the opposite of a equals 0. 0 is the identity element for addition. In multiplication, they're reciprocals. So a times 1 over a is 1. 1 is the identity element for multiplication. The identity function is the function that doesn't do anything. So that's f of x equals x. It's the function that takes in a value x and leaves it right where it is. So if two functions are inverses of each other, then when we compose them together, we should get x. Okay, they should simplify down to just x. So let's go ahead and look at a few examples of this together, and then I'll have you all try a few. So what you want to do is you want to do g of f of x, and you want to do f of g of x. Okay, so in this first example, this would be g of f, so that's g of the fourth root of x. So that's the fourth root of x to the fourth. And the fourth root of x to the fourth is just x. So that's fine. Okay. Then we also need to do, sorry, I'm going to do this a little differently. I don't like how that's spaced. So then we do the same thing for f of g of x. So that's f of x to the fourth. So that's the fourth root of x to the fourth. And this is actually the absolute value of x. Because remember, if you take the an even root of an even power, if I were to plug a negative number in here, I would get a positive result. So I would actually get the absolute value of x. I wouldn't get x itself. So because that's not x, these are not inverses of each other. Because I didn't get x for both of them. Okay, and so that's all there really is to doing this. So let's try the second one here. So I'll do g of f of x. So that's g of 4 minus 1 over x. So we can substitute 4 minus 1 over x into x and g. So that's 1 over 4 minus 1 over x. And then we just need to simplify. So this would be 1 over 4 minus 4 plus 1 over x. The 4's cancel. So this is 1 over x. And that's 1 times x over 1, right? Because dividing by a fraction is multiplying by its reciprocal. And so that's just x. Okay, so that way worked. And so now we can try the other direction. So f of g of x. So that's f of 1 over 4 minus x. So that's 4 minus 1 over 4. Sorry. So now I'm plugging that in for x in this function. So that's 1 over 4 minus x. And just like on the last problem when we had 1 over, that just gives me the reciprocal of the bottom one. So this would be 4 minus x. Distribute the negative. It's 4 minus 4 plus x. Simplify, and you get x. So we got x for both of these. So those are inverses. Okay, so that's the idea here. So we're just doing the composition in both directions, simplifying and seeing if we get x in both cases. So let's try a couple more together. So the next one, we do the same idea, start out by finding g of f of x. So that's going to be g of 20 minus 5x. So that's negative 20 minus 5x over 5 plus 4. I can simplify here, so I can cancel out a 5 from all three pieces here. So this is negative 4 minus x plus 4. Distribute the negative, so this is negative 4 plus x plus 4, and the 4's cancel, so I just get x. And then we can find f of g of x. Okay, so now we're doing this the other direction, so plug g into f. So that's 20 minus 5 times the opposite of x over 5 plus 4. Distribute the negative 5, so 20. Negative 5 times x, negative x over 5 is just positive x. Negative 5 times 4 is negative 20. Combine like terms, and you get x. So these are inverses. Okay. And then the last one, we do the same idea. So I do f, I'll keep doing these in the same order. So do g of f of x. So that's g of x cubed minus 27. And so that's the cube root of x cubed minus 27 plus 3. And that doesn't simplify any further, so that's not going to work. So these are not inverses. Right? It has to work in both directions, so once it doesn't work in one direction, I can stop. Okay, so go ahead and flip over to the next page when you're ready, and pause the video for a moment and try to show that these are either are inverses or are not inverses, and then once you're done, we'll go through them. You can start the video again and we'll go through them. Okay, so here we go. So just find g of f of x. So in this case, that would be g of 4x plus 4. So that's 1/4 times 4x plus 4 minus 1. Distribute the 1/4. So 1/4 times 4x is x. 1/4 times 4 is 1. 1 minus 1 is 0. So that's x. So good job. That one works. And then we do f of g of x. So that's f of 1/4 x minus 1. Plug that in for x in f. So that's 4 times 1/4 x minus 1 plus 4. Distribute. 4 times 1/4 x is x. 4 times negative 1 is negative 4. Combine like terms and you get x. So these are inverses. Okay, and then one more here. We can try this last one. So g of f of x would be g of the cube root of x minus 2 over 5. So we can plug that into g. So that's 5 times the cube root of x minus 2 over 5 cubed plus 2. Cube root cubed cancels out. So this is 5 times x minus 2 over 5 plus 2. The 5's cancel. So this is x minus 2 plus 2. And now the 2's cancel. So we just get x. And then for f of g of x, it's f of 5x cubed plus 2. Plug that into f. So it's the cube root of 5x cubed plus 2 minus 2 over 5. 2's cancel. So this is the cube root of 5x cubed over 5. 5's cancel. So it's the cube root of x cubed. The cube root of x cubed is just x. So these are also inverses. Notice here I had the cube root of x cubed. When we did the fourth root of x to the fourth, it was the absolute value of x. But the key here is with negative exponents, negatives stay negative. So we do not need that absolute value, unlike even exponents. So when we use odd exponents, we don't have to worry about the absolute value, but with even exponents, you do. So that's how you tell if two things are inverses. So now what we want to be able to do is we want to be able to find those inverses. So if we're given a function, we can find those. So if you look back here at these two examples we just did on page 42, what you'll notice here is all of the operations in one function, we find the inverse operation in the other function. So for example, in f on this bottom one, I've got -2. Over here on the right, I've got +2. I've got a divided by 5 in f. I've got a multiplied by 5 in g. And then in I've got a cube root in f and a cubed in g. So one way to find the inverse is by doing this idea of inverse operations, which we call reversing composition. And that's because the order is in reverse. So one really easy way, I think at least, to do these is to look at start with your function f and write out all the operations in the order you would do them. So in this case, order of operations tells me to start with the exponent, so I would do x cubed. And then after that, I would multiply, so I would do 3x. And then after that, I would subtract 7, so I would do x minus 7. And if you were to plug these functions into each other, compose them together, you would get the function you started with. So they go in this order. So then the inverse of that is the inverse of each one of these operations, but in reverse order. So the inverse of the x cubed is the cube root of x. The inverse of 3x is multiplying by 3 is dividing by 3. And the inverse of subtracting 7 is adding 7. And then we do them in the reverse order. So what we're going to do is we're going to plug x plus 7 into here, and then we're going to take that whole thing and plug it into there. So this would be, you start with x plus 7, then you substitute it in here, so you divide it by 3, and then you substitute this whole x plus 7 divided by 3 into the cube root, so you get the cube root of x plus 7 over 3. So there is our inverse function. Okay? And it can be that simple. So you're breaking it down into pieces and finding the inverse of each piece, and then putting it all together. So let's try another one. So in this case, f, the first operation is we add 3, right? If I plugged a number in for x, the first thing I would do, add 3. Then I would take the square root, and then I would subtract 9. And they go in this order. So then we find the inverses of those. So the inverse of adding 3 is subtracting 3. The inverse of the square root is x squared, except there's a caveat to that. So it's x squared, but we cannot, except we cannot plug negative numbers into it, right? Because negative numbers can't go into the square root of x. And then the inverse of subtracting 9 is adding 9. So we're going to compose these together, and we're going to compose them going upwards. So if I do that, my f inverse of x is going to be x plus 9. I'm substituting that into x squared, so that's squared. And then I'm subtracting that into x minus 3, so minus 3. Okay, and then the key for this is that our x's have to keep this restriction in mind. So if we look back, we know that these two don't necessarily aren't exactly, the square root of x and x squared aren't exactly inverses of each other. I can only do part of it. And if we look at the graphs real quick, we can see that. So if I graph y equals x squared, y equals, well, let's do the square root of x first. Y equals the square root of x, so there's my original function. And then if I graph y equals x squared, notice that these appear to be inverse functions and they're close to it, but the problem is the red graph is not one-to-one. This parabola is not one-to-one. So what we actually want to do is we want to restrict its domain. So I restrict its domain and I say that I need x to be greater than or equal to 0. And so now notice that that is one-to-one. And notice that these two graphs look like they're related to each other. So that's the thing I know. Now, the key here is, what happened to the x's in this based on transformations? Well, they get moved, the x's get moved 9 units to the left. Okay, so that means my x has to be greater than or equal to -9. Okay, because this got moved 9 units to the left. So that's one of the odd things you have to be careful with, is when your inverse is not a one-to-one function, you're going to have to restrict its domain so that it is. So in this case, the inverse of the square root of x is x squared. That is not one-to-one, so I have to restrict its domain to only positive x values so that it is one-to-one. Okay, so let's go ahead and try a couple more of these by reversing composition. So the next one, for f, the first thing we do is divide by 3, and then we add 6. So for the inverse, the inverse of x divided by 3 is 3 times x, and the inverse of adding 6 is subtracting 6. Okay, and then we're going to go in this reversed order. So f inverse of x is x minus 6 multiplied by 3. And it's really important that you put those parentheses there so that we do this in the right order. Because what this also could be written as is f inverse of x equals 3x minus 18. And if you forget to put the parentheses and you just get f inverse of x equals 3x minus 6, these are not equal to each other. So this is not correct. So the order is important, so make sure you put parentheses around your operations. Okay? So either of these two answers would be fine. And then last but not least, this one, f. First thing we do is add 4, then the cube root, and then multiply by 3. So for the inverse of adding 4 is subtracting 4. The inverse of the cube root is cubing. And the inverse of multiplying by 3 is dividing by 3. And we're going to do these in the reverse order. So f inverse of x is x over 3 cubed minus 4. Okay. So now that you've seen a few examples of this, go ahead and pause the video and try these 3 examples on page number 44. And then when you start the video again, we'll go over it. Okay, so in this one, f, the first operation is multiply by 3 and then subtract 7. So it's inverse. The inverse of multiplying by 3 is dividing by 3. The inverse of subtracting 7 is adding 7. And we start with the x plus 7. So f inverse of x is x plus 7 divided by 3. Okay. For this one, f, first thing we do is multiply by 1/2, and then we subtract 9. So for the inverse of multiplying by 1/2 is multiplying by 2. The inverse of subtracting 9 is adding 9. And so the inverse function here would be x plus 9 times 2, or 2x plus 18 if we distribute. And then the last one here, our only operation is dividing by 2. So the inverse of that is multiplying by 2. So f inverse of x is 2x. Okay, so that's one way to do inverses. And this works really nicely if you only have one x. So it's really clear what the order of operations is. But that won't always be the case, so we need another method for finding some inverses. And so that method is the switch and solve method. So that's what we're going to look at right here. So the switch and solve method. So the idea, there are basically 2 ways to think about inverse functions. They're either the inverse operations in the reverse order like we just saw, or you're flipping the x and y's. right? That's what we did originally. We flipped the x and the y coordinates. So if you replace f of x with, if you replace f of x by y, and then you interchange the x's and the y's, you will then solve the equation for y and replace y with f inverse of x. And then the last thing you want to do is deal with the domains if you need to. Okay, and we'll look at that here in a second. So check that the domain of f is the range of f inverse, right? Because you're changing, and the range of f is the domain of f inverse. So you're interchanging the x's and the y's, so their ranges and domains should be flip-flopped. So let's just go and go through a few examples of this. So the first one, we replace f of x with y. Then we switch the x's and the y's. Now at this point I found inverses. These equations are not equal to each other. They are inverses of each other. But to find the inverse, I need to write it in function notation, which means I need to solve for y. So get rid of the square root by squaring both sides. Then we can add 1 to both sides. And then we can divide by 3. Okay, and so now we've got the y by itself, so we can rewrite this as x squared plus 1 over 3. Okay. Now, the question becomes, well, what's happened? Notice here, this is a parabola, so that is not going to be 1-to-1. So just like on the square root one we did on the previous page, I need to ask myself, what's happened to the x's here? Well, what's happened to the x's is that they've been moved 1/3 units to the left, right? If you notice here, this is 1 divided by 3, so that will be plus 1/3. So that's negative 1/3 unit. No, sorry, that's not what's happened to the x's. If you notice here, if we graph this, let's go ahead and graph this. I think that'll make it easier to see. So I've got x squared plus 1 divided by 3. And so notice, with the x values, I want to cut this graph in half. Well, notice that the graph has its bottom point at x equals 0. So that's where I want to cut this graph in half. So I want to say that x has to be greater than or equal to 0. So wherever the halfway point of the graph is, wherever it's symmetric, that's where you want to cut it off. And so in this case, that's at 0. Okay, so that's all there is to doing this switch and solve method. Now, this was a problem where I could have done it by reversing composition. And in fact, the one below this here is that as well. But let's go ahead and practice reversing composition again, just so we get the hang of it. So replace f of x with y. Then interchange the x's and the y. So this becomes x equals negative 2y plus 5. And then we can just solve for y. So subtract 5 from both sides. So x... So this will become x minus 5 equals negative 2y, and then divide by negative 2. So it's f inverse of x equals x minus 5 over negative 2. Now, I can simplify this a little bit by moving the negative into the top. So this becomes the opposite of x minus 5 over 2, and then distributing. So this becomes 5 minus x over 2. Okay, and that's all there is to using the switch and solve method. So if you like a little bit more of an equation way, solving an equation format for finding inverses, this is your method. It's not necessarily the quicker way to do it, but it is definitely a way that involves, that's more straightforward when it comes to solving an equation. Now, this last equation here has 2 x's in it. So we have to use the switch and solve method to find this one, because there's no way to tell which operations come first in this, because you have 2 x's. Which x do you do the operations for first, the top or the bottom? Okay, so we can't tell. So that's why we need to use this reversing composition idea. So it'll look like this. So we've got y equals 2x minus 1 over x minus 6. Change the y to x and the x's to y. And then we want to solve for y. So first thing you want to do is get rid of the denominator. So multiply by y minus 6 on both sides. So on the right-hand side, those cancel. On the left-hand side, I can distribute. Now we're solving for y, so you want to collect all the y's on one side and everything else on the other. So I can add 6x to both sides. So it's xy equals 2y plus 6x minus 1, and then subtract 2y from both sides. So it's xy minus 2y equals 6x minus 1. And now I want to get the y's out of these two terms so I can factor. So that's y times x minus 2 equals 6x minus 1. And now I can divide by x minus 2. So we get y equals 6x minus 1 over x minus 2 for our inverse. Okay, so that's the idea. So go ahead and let's flip over to the next page. And go ahead and pause the video and take a few minutes to try finding these inverses using the switch and solve method. Okay, welcome back. Now that you've given these a try, let's go through the answers together. So this will be y equals 3x minus 7. I switch, the y becomes x and the x becomes y. And then we solve for y. So add 7 to both sides. And then divide by 3. And so f inverse of x is x plus 7 over 3. Okay. So now notice in this next one, we have a similar restriction on x that we have a restriction on this because x minus 2 squared is not a one-to-one function. But if I restrict its domain so that it starts at 2, it cuts off half of the graph and it becomes one-to-one. So we don't really need to worry about that for finding the inverse. Except for one step, which we'll mention here in a second. So start by switching the x's and the y's. And then we can solve this. So get rid of the square by taking the square root of both sides. So this is plus or minus the square root of x equals y minus 2. Now, here's where this restriction comes into play. I have two options here for the square root of x. I have a positive one and a negative one. So the question is, which one do I want? Well, I want the one that matches with up here. So are the x's positive or negative for x is greater than or equal to 2? Well, they're positive, which means I want the positive square root. So this will be the square root of x equals y minus 2. Now, if this had been x is less than or equal to 2, then I would have picked the negative one. Okay, so then we can add 2 to both sides, and we get the square root of x plus 2 equals y. So f inverse of x equals the square root of x plus 2. Okay. So that's the idea. And then the last one here is very similar to the last one we did on the last page. So replace f of x with y. Then interchange the x's and the y's and solve for y. So we get rid of the fraction by multiplying both sides by y minus 5. So this is xy minus 5x equals y plus 3. Get the y's all on the left-hand side. So add 5x to both sides. So xy equals y plus 5x plus 3. Subtract y from both sides. So we get xy minus y equals 5x plus 3. Factor out a y. So y times x minus 1 equals 5x plus 3. And then divide by x minus 1. So y equals 5x plus 3 over x minus 1. So our inverse of f inverse of x is 5x plus 3 over x minus 1. Okay, so that's all there is to finding inverses. Now, the last thing we want to talk about in this is the graphs of inverses. So as we just talked about with the switch and solve method, inverse functions simply have the inverse, simply switch the x and the y coordinates of the graph. So, or another way to say that is what happens is they're a reflection across the line y equals x. So if you look at this line, all of the y equal x's, the y's and the x's are the same. So they all look like this. So if you flip those, nothing happens, right? If you flip a and a, it's still a comma a. So those don't move. But all of the other points flip across this line. So they go to their symmetric point on the other side of the line. But we can use this idea of taking a comma b for f, and for its inverse, we just flip-flop the ordered pair to get the new points. So for example, if I were going to do this f of x equals x squared plus 1, I could start by graphing that on my calculator. So I've got y equals x squared plus 1. And I want to restrict the domain, so click and hold down on the circle, the red circle, and it'll let you bring up these settings so I can set my domain. And I want my domain to be x be greater than or equal to 0. And so now that chops my graph off. So now I can get some ordered pairs from this graph. In fact, I think if I want, I can table convert this so it can put it in a table format and give me some ordered pairs. But notice, if I put in, so if I use this as a table view, okay. Sorry, I was just playing around with that. It's not really working the way I expected it to. So I'll just go back to the original graph. So y equals x squared plus 1. And if you want, like I said, you could do the table convert thing here and get some ordered pairs. So if I hold down here, another option is table convert. And notice I want x to be greater than or equal to 0. So I'm only going to look at these bottom 3 options. But that gives me some ordered pairs I can plot. So 0, 1, 1, 2, 2, 5. So I've got my ordered pairs 0, 1, 1, 2, 2, 5. And now, so that would be the function. So I can graph that. And so that looks something like this. And so then to find the inverse, all I have to do is flip these ordered pairs. So 0, 1 becomes 1, 0. 1, 2 becomes 2, 1, and 2, 5 becomes 5, 2. And we can plot those, 1, 0, 2, 1, 5, 2, and we get the inverse graph, which notice is a reflection across this line. Okay? So that's all there is to doing these graphs. So let's try another one. So if I do the opposite of x cubed, right, I can do y equals the opposite of x to the third power. And that graph looks like that. And once again, if I want to have class calc give me some ordered pairs, I can just table convert it. Okay, and it gives me a bunch of ordered pairs there. So I've got -2, 8, -1, 1, and so on. So my ordered pairs for this one are -2, 8, -1, 1, 0, 0, 1, -1, and 2, -8. So that looks like this. And then if I find its inverse, I flip those ordered pairs. So -2, 8 becomes 8, -2. -1, 1 becomes 1, -1. 0, 0 is on that line y equals x, so it stays the same. 1, -1 is -1, 1, and 2, -8 is -8, 2. So that would look like this. So I got 8, -2, 1, -1, 0, 0, negative 1, 1, and negative 8, 2. So its graph looks something like this. Okay, and so that's the idea. So go and flip to the next page and pause the video, and using your class calc app, give these graphs a try and see what you get. Okay, so now that you've given these a try and you've started the video back up, here are some ordered pairs for F. So for F, we probably get 3, 3, 0. Wait, yeah, 3, 0, 4, 1, and 7, 2. So that looks like this: 3, 0, 4, 1, 7, 2. And then its inverse would be 0, 3, 1, 4, 2, 7. So 0, 3, 1, 4, 2, 7. So it looks like that. Okay, then the next one we could use, I'm not sure these are going to be the same order pairs you all got from class calc, but I'm going to use negative 2, negative 4, 0, 2, and 2, 8. So that looks like this. So negative 2, negative 4, 0, 2, and 2, 8. And so then F inverse would be negative 4, negative 2, 2, 0, and 8, 2. And notice, if these do intersect, they're going to do so on that line y equals x. So in this case, these two intersect at negative 1, negative 1. Okay, and then the last one, F will get negative 2. Oh, sorry. I cannot plug in negatives, right? Because x has to be greater than or equal to 0. So let's start with 0. So 0, negative 4. 1, negative 3. 2, 0. And if we wanted one more, we could do 3, 5. So that looks like this. So 0, negative 4. 1, negative 3. 2, 0. 3, 5. And then the inverse then would be negative 4, 0, negative 3, 1, 0, 2, and 5, 3. So negative 4, 0, negative 3, 1, 0, 2, 5, 3. Okay. And so that's all there is to graphing these. So this is the last section video for Chapter 2. So make sure you're doing all your homework as posted on my math lab. And remember, from now on, I'll just leave it at that. So have a good one. If you need to contact me, if you have questions or concerns about this, remember you can always email me, text, or phone call. And also watch out for my upcoming virtual office hours.